Chair's gone. Any takers? Hands up. You're going to be like that. Not that big. Hello, come in. It's all good news. When that thing gets to the end, I'll be quite happy. It seems to be taking its time. Yay. Yes. Yeah, I'd rather this opened up though. It opened up this morning, didn't it? Ooh, natural hubbub stops. Ooh, there's more faces this afternoon. I'm waiting for this. So if it doesn't work, well, I did that, and now it's doing this. Worst case, I'll get it. Okay, so let us commence. Thank you very much. Right. If I'm hungry, I know where to go. All right. So, this morning we covered a few things. I also gave out copies of the energy, how the energy industry works. You've got that. Those of you who haven't got a copy, I know for a fact I've put another 10 to 15 in C62, but behind closed doors is another 500. So you will get one if you want one. Just go and ask in C62, or I'll bring some more. Next announcement. Yay, the tutorial to boost attendance and dedication to the cause is upstairs in D1 and D2 at 3 o'clock. I'll see whether any more turn up than they did last week, but at least 70 brave souls have walked down the road twice in 2 weeks now, so thank you for that, because the thing will be at EBL. Last announcement. We're into the last phase. Next week is a lecture, and unlike the handbook, it is of course on the timetable. It will be 10 till 11 and 2 till 3 next week with a tutorial upstairs. Remember what I said, the tutorials are all linked to exam questions. Today's tutorial is no different. Okay? Those of you who did last week's tutorial, remember that the exercise and did it quickly, or went, yeah, that was quite good, we did it quite quickly. Well, you did it because you were scheduled to work within 45 minutes, which means it was a scheduled exam question. You did it within 45 minutes. Very good. So this morning we did the green bit in part. We covered the catalyst shapes, we looked at them, we talked about a few things design-wise, but for our guests, they can look in the handbook and look what you missed. But you remember we were talking about different pallet shapes, and we were talking about steam reforming catalysts, and then we were talking about spherical catalysts, and I've got the examples with me. I also have brought them again. All being well, I haven't lost one, I don't think I have, so I'll hand them out. And we'll talk about those real catalysts in light of the process of steam reforming, and then we'll look at a little bit of the chemistry, then we'll talk about the basic techniques that I use and people who work in the industry use to talk about surface area, porosity, and basic measurements. It's an important skill to know about these techniques. I am not expecting a class of engineering to know, other than the title, what they basically do and how you basically carry out the tests, and that's within the notes. But there is a little bit of extra reading you might need to do. I wouldn't dare recommend Wikipedia as a source of information, but you will find some good explanations on X-ray and SEM on Wikipedia, but there are other places to look. Okay. So, we're going to go into the red zone. We're finishing off the green zone first. So, hydrogen production, steam reforming. Some of you have already got design processes, and you know, because you're asking me in class, about various catalysts. What do I do with syngas? What do I do with the shift reaction? Well, here's the process laid out as of Johnson and Matthey's website. Johnson and Matthey have some interesting materials on there. Other people do as well. But if you've got an interview coming up or an assessment centre, and some people do this weekend, Johnson and Matthey Catalyst, this is a good website to have a quick look at. So what have you got? You've got steam and hydrocarbon feed. Remember that I showed you the chunky catalyst this morning. So the nice steam reforming catalyst. That one, just the front row to be passing it around. Please do pass it around. So the chunky catalyst that goes in there is basically because you're going to burn in oxygen and steam. You're going to burn a hydrocarbon. So, like your Barbie, it goes up quite quickly and it gets to very high temperatures. You then move across because you've done your oxygen, you're sticking your oxygen in, you're taking your hydrocarbon, putting oxygen in there, you've got to do high temperature shift, low temperature shift. Don't worry about the chemistry this minute, we'll show you what that is in a minute. And then Further removal of CO2 by pressure swing, so engineers know about pressure swing absorption. If you don't know now, you will do next year. And finally, the last catalytic step, which is methanation. The whole aim of this process is to generate pure hydrogen. It's an amazingly robust catalyst that you're handling, and it's an amazingly unsophisticated one. Then we've got the high temperature shift and the low temperature shift. So let's have a look at that. So, what I want you to look at, and I'll put down the pointer. Try not to take anybody's eye out with this. So, basically, if you're looking at this, this is the high temperature steam reforming process. These two here are high temperature shift and low temperature shift. Look at the drop in temperature, 800 degrees C to 350 to 200 degrees C. So these catalysts look totally different to this one, because this one's having to perform a high temperature, highly expansive, contracting process, lots of heat transfer, lots of difference in transfer. It's basically done in a shed. The shed is 3 stories high. This shed has rods that are suspended from the ceiling with the catalyst in them. A little man or woman goes along and walks across the shed and peers in a viewing window and looks in. What do they see? They should see nothing. They should see the hang-down tubes, which are dark. In the corner there's a red one. What happened? It broke. So the burning process has now got out of the containment of the tube, and it's actually got to be replaced. So they will shut down a section, and they will go in and they will change a hanging tube of catalyst. But that's how they determine whether the catalyst is working or not working. If it's dark and they're getting the product, it's working. If it's red, it's burning, it's broken. That's just one tube in a stack of 300 tubes, but you're literally about the size of the shed, and it's 3 stories high. The size of this lecture theatre, and it's 3 stories high. That's what that process is. Brutal is what that process is. No sophistication whatsoever. Burn it, it goes as hot as it wants, and your product comes out the other end. Basically what you're trying to do is you're making CO and hydrogen, which is here, and then that CO you're trying to get rid of to give you more hydrogen, and then you can get rid of the CO2 by pressure swing. So all high temperature shift and low temperature shift are doing shifting the equilibrium with different types of catalysts to end up with more. So for the ones on the front row, you get the personal service. Okay? You can see the difference. It's sort of greenish. Okay? And it's reddish. Okay? Take them, pass them back. Those are the 2 catalysts you see there. The key thing from a chemist's point of view, or from Johnson Matthey point of view, is how are they made? And they're made from iron with chromium, and it's rocks. Rocks dissolved in acid, acid changed to acetic acid, heated up to give you the oxide. The oxide is then dried from a wet slurry paste into a powder, and then it is pressed and pelleted into that shape. Just like you would make a medicine, you do the same. Just press the powder, make the pellet, and away you go. So, key bits, CO level, 15% to 2%. Last bit, 2% to 0.2%. After that, you hopefully got pressure swing, which takes out all the CO2. You're left with very pure hydrogen. If you have to do any more, it'll have to be to get rid of methane, and they call that the methanation or demethanation process, and that's right at the end. But that's the basic chemistry. Look at every equation there. You're faced with this in design project next semester. Lots of little reactions that are equilibriums. Arrows going both ways. Lots of little steps along the way. But the bottom line is, you've got a completely different catalyst. You've got a constraint of physical strength, which means when you say to me, but Arthur, the catalyst is supposed to be really effective. We want it to be 100% effective. You can't be 100% effective. You can be 90% effective. But in this one, you're giving up 90%, and you're going maybe for 50%. Or you're going for little. Because you've got to have it physically strong to withstand that 750 to 800 degrees C process. So 3rd year chemical engineers, the big problem for you guys and girls are simply too many options. How do I limit my options so that I know what my best catalyst is at the end of the process? You will say, well, I know this paper, and I know this paper, and I've got this stream of stuff in the middle that's suggesting I do it that way, but these 2 are quite interesting on either end. My mother used to have a very good anecdotal story. You ever go into a doctor's office and they say there's something interesting about your medical condition, run the other way because they don't know what it is. Go find another doctor. Because you don't want to be interesting to a medic, because they don't know what to do. Because you're interesting, because you're not boring, you haven't got a cold or a sore foot. Same thing in the way of catalysis and processes. If you've got two very interesting ones, be very nervous. Be very nervous about having interesting, and go for boring bulk of information in the middle. Now, some of you have been approaching me with some really nice ideas for catalysis and nice ideas for reactor. I've just heard one about a spinning basket reactor instead of a slurry reactor. All very interesting. You'll update me at the end of the lecture, I'm sure, as to what you found out at 1 o'clock till 2 o'clock. Did you do anything? No, you didn't do anything. I knew you wouldn't, but never mind. I promised I'd get feedback on something for somebody, and I didn't do that either, so naughty boys, both of us. Okay, so she'll come chasing me in a minute. I know she will, because she's in the audience. So we got the idea. Design is about choices. You have to select them. Remember, if you make a bad choice, and a lot of you are nervous about making a bad choice on design, doesn't matter. You make the wrong choice, but you justified it, and the justification seems sensible, you get away with that because you're learning. And in industry, you'll have a team of designers who'll be saying, oh, I'm not so sure about this, I'm not so sure about that, and they'll be ruling out options, and it will be okay. Because you'll come to a consensus based on other people's experience. Remember what we said about the steps in a heterogeneous catalytic reaction. It's still current. We've got the chemical going in, A, and B coming out. Remember the different steps we've got. Remember the little heart or the marriage counsellor or the catalytic site. Before you asked me about this, and it was obvious that you weren't quite clear where the active metal was and the active site. This morning, we talked about how catalysts deactivate. We talked about sintering, we talked about coking, we talked about collapse, and we talked about the metal all agglomerating in the middle. But still remember that diagram, because you can sketch that diagram easy enough. You can remember the steps, first across the mass transport, across the boundary layer, diffusion through the pore. Obviously, the assumptions are that the pore is a straight inkwell channel. We now know that's not correct, but it's our assumption, and it's our model, and it's what works. The straight channel, which is obviously not straight, so it's tortuous, you've got bendy movements, goes to the active site. The reaction takes place, 3 goes to 5, and then out come the desorption steps, and the diffusion, and across the mantle. Just remember that, and everything you do, with regards to this course, and the whole course gets put onto that one, and last week, you remember the last slide, I said the whole course is there with that Arrhenius plot, which that man at the back will have taught you at some point in CRE 1, won't you, Sam? So, metal location in catalyst. Eggshell versus homogeneous. Now, there's a little bit of confusion about where the active material was this morning, so this one helps bring that back into focus. Last reminder, and then we get on to some new stuff. So, if the black layer is on the outside, and it's an eggshell catalyst, it's not homogeneous. But what this slide is trying to show you is the move from eggshell to homogeneous catalyst. Eggshell. So this is our imaginary pore. This is the surface of our catalyst at the top where the red blots are. That's our eggshell catalyst. When you ask me where's the active site, you've still not got it quite right. And you asked me this morning, so we'll still try again. The active site can be anywhere, in or outside the structure. We try to design them so they go in specific places inside the structure, as well as solely on the outside, solely on the inside, and this is trying to show that with a schematic, so that the red dots are the platinum sites from this morning, and here it's homogeneous, it's all the way through the pore. Here it's on the surface and it's an eggshell catalyst. And this is an intermediate. If we get all the material in the middle, it's known as an egg yolk catalyst. I'm not kidding. We're engineers, here's what it says on the tin. Are we happy at this point? Great. Don't believe you, but great. So, you send things off to be measured when you're in. Yes, sir. Sorry, I saw your hand just at the last second.
Yeah, just about the previous one. You said we assume for design that we have an equal pore. Like when we're designing, we're
Stop.
assuming.
Rephrase. So, we have we have 2 things you really got to remember, which are the active site model, and you've got the active site model and the pore model. The pore model, we are assuming an inkwell, so it's sides straight down, filled. Then it fills up, and that's the way we look at it. What's your question now? Having just said that.
How do we take into account stuff like the real life torch velocity?
So back to the rule of thumb again that engineers often apply. What's the voidage in a reactor? Go on, what's the number? Doesn't matter what it is, what we pack. Anyway, what number are you going to tell me?
0.5.
You're going to say 0.4 to 0.6, and 0.5 is going to be your average value, right? So now we're going to assume that if the pore is tortuous, like an Amazonian river, yeah, or the Amazon itself, in fact, so it goes like that, then it's twice the distance. So the pore length is twice. So the worst case scenario is it's twice as worse as we think it is. So we're going to assume a model based on a straight pore because it makes it simple for us. Then we're going to make it twice as worse. Okay, what do engineers do mostly? What do I always kid you about? You always make it 1.5 times bigger. Why? Well, because it's a safe thing to do. You allow for the expectation that something's going to go wrong. And we'll just make it a little bit bigger. You just don't want to get carried away making it too big. Okay. Answer your question? Good. He and I will be doing it next year together, by the way, just so you know. Okay, so chlorine slide, know that. Key things on it are all the techniques to probe on a molecular level and to delve in. So you're moving from your world to my world in one step very quickly, so you're not going to like it. Put your seatbelt on, buckle up. Okay. Morphology, SEM. Morphology, what does the surface look like? So we're talking about, is it a rough surface? So is it a smooth surface like that? Or does it look like the seats and bumps of the Himalayas, the troughs and humps of the Himalayas? So chemical analysis, what does the surface chemically look at? Okay, we want to know how much platinum we've got on it, but did we put the platinum on the surface as an eggshell, or did we put it all through the structure? Phase characterization, XRD. We all know what a fingerprint is. We've all seen CSI. So for me, taking an X-ray of this thing is like taking a fingerprint. I'll explain what that is in a minute. So we want to determine what the surface looks like. We want to look if our metal's been dispersed. We want to know if we've got the right material. And then we perhaps want to do really fancy things, like look at it with a super magnifying glass and use a transmission electron microscopy technique. Or we even want to probe what oxidation states it's in. Why is this important? Oxidation state is important because if it's the wrong oxidation state, it might not do your reaction. Certain companies have a lot of problem with changing oxidation states. So in other words, something left out in the atmosphere will oxidize. So we end up with rust when we've got raw iron. Same is true for catalysts. So we like to know about those things. When we want to look about the surface area of a structure, obviously this is a molecular model. We call it a ball and stick model in the trade, but it's obviously a model. We want to know how much space is on the inside of this. So we want to probe it with a molecule that fits in. So nitrogen is a pretty small molecule, hope you agree, and it fits in just nicely, and we're able to do something called a BET analysis, which is named after the people that invented it, to do the surface area. Pictures of kit are always very exciting, I find, more important to the results. So I'll show you the kit, and you can look it up. Scanning electron microscopy, you're just doing a beam of electrons across the surface, and you're trying to image the topology and the surface of the structure. You can then use a technique which is known as energy dispersive spectroscopy, which is EDAX to me, and it will allow you to get the elemental composition. So very nice techniques. Where is the nearest one to you? It's on B floor in the mill. Okay, so there's one in the mill. There's loads of them in the materials science building, which you walk past to go to the James Chadwick. So we're very well equipped and very fortunate at Manchester to have quite a few of these babies. And as you can see, it's virtually a benchtop machine. I have to say a long time ago that was not true when I was a lad, but now it's a benchtop machine. You used to have a little camera on it that you used to take photos with, and I had to go to a dark room and spend 2 weeks of my life developing 10 photos. Now you get 10 photos in about 10 seconds going click, 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 click on a mouse. Doesn't mean to say your data's any better. You cared about it when you had to develop your own photographs, I tell you. It also helped if you knew if anybody else was in the dark room at the same time, which was very disturbing, I can tell you now. Anyway, moving on. So, morphology. So here is a pin. It's not really, it's a scientific experiment that I carried out. So this is a picture. So imagine the pictures you could get of an SEM. An SEM is a scanning electron microscope. It's a microscope. It magnifies things. The common picture you see on the web is a fly, and the compound eye of a fly. And it's a fabulous image, and everybody knows it. It appears regular in science fiction movies. But So this is actually a 0.5 millimeter wire, 0.5 millimeter. So it's about the same size as a pea diameter. It looks like it's just a bit dusty. That's all it looks like. And that is what the surface looks like when you magnify it up. Now then, engineers, this is the bit you've got to have a leap of faith with me. So when you put this magic dust inside a reactor and you say, chemist, can you tell us which one's the best catalyst? And you say, well, I don't know. There's a bit of difference between these catalysts. You go, I don't care. It's that one over there. It's A, B, or C. This is what you're doing to my life and my research and my whole career to date. You're just putting it straight in the bin, straight away, and you're saying that the pin looks like it does on the left-hand side, but you've not got an appreciation of the right-hand side. That is massive surface area that you've got there, but the rod is just like a pin that you would put in a piece of paper or in your hair, or to tack something together. It's that dimension. I hope you like the image. It took the poor girl a few years to get that in her PhD, but it's a very nice image. Here's one I made earlier. So here's the same pin, except now we've got a zeolite catalyst growing on it. Now we've got two different structures there, one of which was an alumina structure, which looked very nice with its platelets with a large surface area, and now that's one of the zeolites that I will tell you about next week, which is grown on the surface of the same pin. That is that. That looks even less like that than the previous picture. The other one at least had the decency of looking a bit frosty. That one has actually got that grown up. Now that doesn't come off. Okay, that might, because it's a bit woolly and a bit thick, but if I do it right, it doesn't come off. And I presented that last month in Bahrain, when you saw I disappeared off for a week. So I use these tools, you use these tools when you're in industry, people advise you in industry. So the next thing is the pores, the number of holes going through the system. Of anything other than a lot of holes going into a central compartment of a catalyst. But it gives you an idea of the different sort of pores you can have. We can have all sorts of materials. Imagine that now just sprays out and the molecules go everywhere. How much is the internal area of that? Put it another way. Here's something that you use every day that you probably never knew existed. You use a malabsorption sink. Okay, zeolite A. It's a zeolite. It goes in washing powder. It has one key characteristic. It likes to ion exchange things, and it loves to pick up calcium. It loves to pick up calcium and drop back in sodium. So if you live in a hard water area, which is the northeast, why would you live in the northeast when you can live in the northwest, in Manchester, of course, where it's beautiful, soft water, and it never rains and the sun always shines, I ask you. So, allowing for the fact that that is zeolite A, it's in washing powder as an aluminosilicate. It's the highest bulk zeolite catalyst. It is worth millions, billions in the detergent industry. They're forever trying to improve it and make it better. Engineers, you know it as a mechanism of being able to separate nitrogen and oxygen because the pore or the hole inside is so small, that window is so small to get in there that you can manage to separate nitrogen and oxygen, which are pretty small molecules. So it's important for us to know the size and the number of the pores. Now you're holding it, and if that young man puts his hand to the hole, okay, we'll see whether you can put, you don't have to do it suggestively, you can just put your hand. Brilliant. And you demonstrate ably by only managing to get a few fingers in there. We will not go any further. Inside there we have a bigger area, do we not, sir, than we have on the entrance pore, yes? I already nailed that lot earlier this morning, didn't I? When you were giggling away to your heart's content. So, have a look around, spread it around. It's a zeolite. The next technique is going to be very important for that actual zeolite structure. So your surface area then, so how many holes we've got in it, what's the overall average? More importantly now, size, number, high surface area, small number of pores. What did we talk about this morning? We talked about the structure actually, what did we say it was? It was So we had sintering, we had coking, we had... Yes, but what did we have in relation to pores? You said it yourself. What's the difference between? Fouling. So fouling was the key product. What is fouling? Well, imagine that thing's got a very small hole, but it's also got a big internal cavity. But the hole in the middle could get full, and it could be trapped. So if we get something inside it and it's reacting, it might be big enough to make the reaction happen, and then it gets stuck, and you're not going to get it out. So now it's foul. End of story. Got to get rid of it. So small pores give you big surface area. Big surface area gives you great catalytic benefit, as it says there, but you can also have a big problem with the structure fouling. So it's a problem. Now then, where did we cover that before? The lecture, or one before now, which was on effectiveness, diffusion in catalytic reactions. So go back to that chapter, and this one links to it. So this is the way we do it. How do we do it? Well, what are we first trying to measure? Physical and mechanical properties by density. Bulk density, particle density, solid density. I've never used the term solid density. I've always used the term skeletal density or true density. So that's just the density of the structure. So wherever the model is, where's the model? Yes, young lady, you're holding the parcel. Hold it above your head, please. Very good, very good. Yeah, hold it above. Go on. You're embarrassed, but do it anyway. Right, so you're holding it. So basically what we're talking about now, engineers, what was the voidage that we said, 0.5? Right, how many holes do we think is in that structure? How much of that real material is solid? And the answer is about 30%. The rest are pores or voids within the structure. So you've got the particle packing in the bed loses you 50%. So you've now got a space, it's 50% full of space. Your structure is 70% full of space. So hold on a minute. We were going to put in 1 ton, and now all of a sudden we're going to put in 3 or 4 tons because we've got to allow for all the space we've got around the catalyst. So is the size of our reactor now right? And can we build said reactor? So that's the importance of those 3 characteristics there. Bulk density, particle density, and skeletal density. And I should always remember to be in the right place when I stop talking. So the things that we're really interested in, and you will find are really a nightmare for fouling of catalysts and other things, are macropores, mesopores, and micropores. The thing that's being carried around, which has just fortunately gone from Roger, bless him, to the lad in front of him. So if that lad now holds up, can you now hold it up again? Okay, so now hold it still now. So you can go onto a website, which is the IZC website, the International DLI Conference, IZC website, and you can get a load of these models and play around with them to your heart's content, and you can move them around and look about the hole. The hole we're talking about there is a micropore, so it's the one at the bottom. Average diameter is less than 3 nanometers. In the case of that one, it's 4 angstroms, 0.4 nanometers, 0.4 nanometers. And what's the size of a benzene molecule again? It's bigger than 0.4 nanometers, so it won't fit in. So another thing that that's famous for is separating isoalkanes away from N-alkanes. So in other words, straight chains versus something with a wiggly bit on the back of it, so it won't fit. So we're talking about molecular sieves, and they're microporous. Macroporous, and you're talking about bigger roadway junctions, more like motorways through the structure. And then finally, macropores are massive holes through the structure, like 6-lane LA highways going through this particular material. And these tend to make the structure very weak. And also they tend to collapse. So you can get macropores and mesopores within aluminas that we were talking about this morning. And I did talk about long range and short range order, so I'll bring that back to you in a second. How are we doing on time? Not bad. So, porosity. So there you go. I've just summarized the bits that I think are important. 30% solids, 30% pores, 40% voids. So the catalyst that you're putting in your reactor is now 30% solid. And the key things are the holes through the structure that allow diffusion, and then the active site to be somewhere dispersed within them. Macropores, mesopores, and micropores. The schematic is trying to show you the difference and the way that the particle clumps together, and he's trying to show you that each one of your solid bits has got holes in it, you just can't see them. That's why I showed you the example of the wires, so you could see the surface difference from what looked a smooth surface to one which was quite completely different. And that's exactly what you don't see when that magic dust gets sprinkled in that reactor. So you treat it badly, or you treat it mean, doesn't keep it keen, it just destroys it, okay? So how do we probe this? We said we use nitrogen, a molecule that's small, and we allow it to build up in a sample. So look at the diagram on the left. I'll talk you through the temperatures at the top. One of the useful things that you will find when you're looking at the literature for design projects and for other things is if you can find that people have done it by a standard method. Somebody's done it by a particular routine and they've done it the same. Normally what happens is you've got 50 labs around the world working in catalysis. 50 labs around the world working in catalysis do it 50 different ways. Except there are some basic techniques we have to do the same way or we get a different answer. The problem is, guys and girls, you are all going to read the literature and decide on who's done it best and who hasn't done it best, and you have limited knowledge. When you get wiser and older in industry, you might have more experience, but when you're making your design project choices, you may not know which one's the standard technique. But if you see the words ASTM, American Standing Testing the Materials Standards, or you see the words DIN, which is the German equivalent for standards, or you see British Standard for BS, then you know that those have gone through an institute. Okay? So if it's an ASTM method, it's gone through an institute and it's a technique that's noted. And this is a particularly old and established technique, but what it's basically doing is allowing you to change the partial pressure of nitrogen through the solid in a sample holder. Just increase the nitrogen, watch the absorption as it goes up, the V for volume absorbed on the left-hand side. As you increase the partial pressure across here, you're going up and you're following the arrow on the way up. The key thing here is that when you try to desorb it, it doesn't come back down the same axis. Now it could come down the same axis, and if it did, there'd be no hysteresis, which is what that region is called. You'll be covering this next year in ion exchange and adsorption, because it's a classic technique, and Flor Sipperstein covers this. The key thing is, why might it get stuck? You know the answer. You personally, definitely. Anybody else know the answer? It relates to the question on core models. Tortuosity. The Amazon River. So it doesn't have a straight path, so therefore it doesn't go in and it doesn't come straight back out. It goes in, it wobbles around a bit, and it can get stuck in the nooks and crannies of the pore. So that's why we know it's not true, but we use the model which is the best model to describe our engineering design. So we've got a nice isotherm there, which is for a typical alumina. It's done at 77 Kelvin, so it's quite cold, and the nitrogen goes in, and the nitrogen comes out. It talks about a monolayer region and a multilayer region on there. Monolayer assumes that just one atom sits on the surface. Multilayer means lots of atoms sit on one another. That is what I want you to take away from that. There are at least 5 types of isotherms. It's just my mind's gone blank and I was trying to think of the 6th one, but I've seen a picture, I'm sure, with 5 of them in, and they describe most porous solids you're ever likely to come in contact with. What are we doing? We're using that graph to determine the amount of space. We're going to draw a line maybe from here to the axis to give us the volume. I'm going to use the following equation to do that. Now, I'm going to let you do a reconnoitre of the literature around that yourself because it's interesting, but it's also a bit boring to cover in the lecture. But I want you to get out this table and remember this table. Those of you who did last week's tutorial question or the week before's tutorial question, you were asked to pick the most diffusion. It wasn't resistant, it was the opposite way around. What was the one that was least resistant to diffusion? And most of you picked the one that had the widest pore. The widest pore meant that it had the lowest surface area. You were then asked which was the one that would have the most activity in the reaction, and you all picked the one which had the highest surface area. So you went for the largest surface area in meters squared per gram. So you've got zeolites, activated carbons, and then, ooh, there's a mistake. That should say Al2O3. Sorry about that. Just spotted that. That's in a textbook, so that's a scanned image from the textbook, so you can see textbooks are not always right. And Arthur's not sharp enough to notice that should say AL203. So correct that if you would. But you get the idea that depending now, cross-reference that table for the table I gave you in lecture 2, which was one of all the industrial processes that you saw. You saw all the industrial processes. We said that 29 of them had catalysts. Of those, 21 were fixed bed reactors. And after that, we had some specialized reactors. If you cross-reference those processes, you will see some of those catalysts, those processes there, and some of those catalysts. And therefore, you've got a nice crib sheet for when you're doing design project next semester. You've got a set of catalysts and a set of surface areas for the particular process that you're using. We're not far from the end. Hold on in there. X-ray diffraction. Don't read all the slides. What does the gizmo look like? It's got 2 arms. It's got one with a detector on it, and it's got one with an X-ray beam on it. Where do we have these machines? We have quite a few of these in chemistry. I use those all the time, so do my students. And basically the sample in the center, which is that disc in the center, is a powder. We bombard it. Where's the structure got to? Who's the lucky person with the parcel? He's just got rid of it. Unlucky young man. So I will hold it to save you the benefit. So now, what does X-ray diffraction do? We're now looking at the surface as if we were the X-ray beam. Okay, so with the X-ray beam, we're going to bounce it in. If it hits the solid atom, it comes back. If it doesn't, it goes through until it hits the solid atom and comes back. It gives us the fingerprint structure that we need. So XRD is about bombarding that structure with X-rays so that if they go through the crystal structure, so if you did salt, for example, that'd be a nice crystalline structure and very uniform, so you know exactly what you got. With a zeolite, you can see, just you guys looking at that surface there, quite lots of bobs and bumps and holes. So if you hit the atom, it will bounce back, it'll reflect. If it doesn't, it goes in. That one will go a long way because it goes to the opposite side of the structure until it hits an atom and comes back. So it's a fingerprint. So that's an X-ray beam, X-ray diffraction, and it looks at the bulk crystallinity, or it's a fingerprint. Is it crystalline? Is it not crystalline? Is it what we expect? If we design a catalyst that's beautiful and costs a fortune, we want to know when we put it in our reactor it is the same as what the manufacturer had told us it was. And that's the purpose of X-ray diffraction. Have a read of the words, have a look on Wikipedia, and remember what you've done already. But you should remember 2 key equations, but the top one is the one I want you to remember for now. It's the classic thing. Anybody going anywhere near Johnson and Matthey will be asked about possibly what they know about crystalline structures. You will definitely be asked what the Bragg equation is, because they don't change much. And when I had an interview there when I was 21, they asked me as well. Fortunately for me at the time, I did actually know. But then I proved to be allergic to something, so they didn't want me to work for them anyway. Possibly work, but we won't go into that. Right. So that's the idea of an X-ray pattern, and what's happening here is this is that arm on the X-ray. So the arm is moving from a low angle up to a high angle, and that's what you're seeing here. You're moving from not quite naught, because it never starts at naught, but let's say 2 theta up to 35 2 theta. And where does the theta go? It goes in the sine bit at the top. Okay? So that's the equation. That's what an X-ray diffraction pattern might look like. There are loads of them around. You can look them up. Because if you are at an assessment centre and you do say you're doing catalytic reaction engineering, it's kind of nice to have some techniques on characterization in your locker. Okay. What does a real XRD look like? Well, here's something that we prepared last year, and that's interesting. Now, why is that, I wonder? We have something happen that's quite unique. I've not seen that before in my whole life. So I have the same slide, but on the one I've got a different talk to the other, which is quite impressive. All right. I don't know what's happened there. So if I make that main page, PC, what have we got? Still got the wrong one. Which one's that? Left or right? Yay, I killed the right one. Okay, guys, we'll see whether it moves, shall we? No, it doesn't. We're going to focus on the left one and we'll look at the lovely XRD pattern while we're at it. So, X-ray diffraction, what you can see on the X-ray diffraction, or what I was trying to show you in both screens, apologies now, is that you've got something that's growing with time. So what we've got is the first one. Let's take the green line, because I don't want you to understand, and it's not in your handbook, so that's why you can't find this. The 8-hour sample there is a horrible wiggly mess. As we go with time, in this particular reactor that we're synthesizing this material, the peaks grow. So that's what I use it for. You can use it to tell if you've made something in a particular time frame and it is what you think it is. And that's what we do. I'm showing you that one because it's something that we did in the lab last year and it just got published the other week. Transmission electron microscopy. It's kind of handy we've got those two together. X-ray diffraction tells us about crystallinity. So what does crystallinity tell us? If you've got a structure that's not crystalline, but it was crystalline, then you've sintered it or mechanically destroyed it. So all this morning's lecture is now coming in with the examples. Transmission electron microscopy, what is that? That's a more powerful microscope than the SEM. Look at the dots, the black dots around the surface of the structure on your left. The black dots are all around the edge and they look beautiful and they're beautifully aligned and some loving chemist has made that for you. And what have you engineers done? You've gone and stuck it in a reactor and what have you done to it? You've made all those little black dots form little black circles. And you've ruined it because it was brilliant. It was beautiful and it was brilliant and now it's not so brilliant anymore. What are the channels that you're looking at? You're looking at the pores in that particular material. But what you've looked at is the metals doing what we said this morning. Do you remember I showed you little red dots and they moved together and they sintered and they made one big dot and they lost surface area. That's exactly what's happened here with vanadium, which is vanadium oxide, B2O5, on anatase, which is TiO2, which is an oxidation catalyst. And by using it, you've actually lost a significant amount of surface area. You can imagine that the chemist was so thrilled with that he thought he'd give it to his engineers because it's the best catalyst he'd ever invented. You tried it once and it ended up being just the same as all the others because all the metal pulled together into a little ball. And you say, thanks very much, but actually it didn't improve. Too bad. And that's usually what happens. Okay, but that's a really good idea, a great picture of metal sintering. However, I've got one better. I'm looking at the time, we're almost out, which is perfect timing. So this one's done on Titan. No, it's not done on a moon or whatever. It's done on Titan in the Materials Center. A lady called Sarah Haig, who is an extremely good lecturer, unlike me. She is a belting lecturer. She is in charge of a particularly high-res, atomic resolution machine. So you're looking at atoms clustered together. Look at the black and white version of it. If you look at the black and white version of it on the left top, hopefully even at your massive distance away, you will see speckles of dots. You'll see a big lump at the top. Used, not used. Used, not used. So the moment I took that beautifully dispersed, half dispersed. So now let's factor in another thing. When I say it's well dispersed and it's 50% dispersed, it means there's 50% of it is a big lump. 50% of it is brilliantly dispersed, but still 50% is a lump. But after I've used it for about 160 days, it ends up being two big lumps. The green and the orange one are just trying to show it you as an elemental mapping. So not only can we see it, but we can tell you what the elements are that are in it. And that just happens to be platinum, and the A stands for aluminum. So it's aluminium. Okay, before and after. But I wanted to show you that because it's not like we don't do these things at Manchester, and it's not like they just came out of Step Books. We do these things. Last technique, thermal analysis. Now the man comes in with his coking now this morning, so we had, how does the catalyst deactivate? We get coke on it. We use this technique to get rid of the coke. There are 3 or 4 different techniques. There are 2 I really want you to remember and have a look at, which are TGA, thermogravimetric analysis, and differential scanning polarimetry. I want you to focus in on TGA. If you were asked, let's say, in an exam question, describe what TGA is, I would expect you to have some idea what it was for, what you did with it, and how it benefited you as the engineer on a process. So what is it? It's a furnace with a balance suspended in it. So on the little boat, the little bucket in here is connected to a balance arm with 6 figures. So it will tell you down 0.000001, maybe another 0 in there, how much weight is lost if I heat it up. So thermogravimetric analysis, heat it up, watch it lose weight. What's the benefit? If we've operated a catalyst, go back to our basic diagram over here. First activity, time equals 0. Activity where time equals t and t can equal 4 years. The amount of stuff that's stuck on that catalyst at any point along this graph, at any conversion, at any time, we can heat a sample of it up. How much comes off tells us how much contaminants we've got on there. Put it another way, it's like watching a clock tick. So if we heat it up and we analyze it and nothing comes off or very little comes off, well, we're early on the time cycle. If we get a lot to come off, we've got to change that in another 6 months, and that's like 9 months earlier than we expected. This is now a problem. So it's like looking at a clock. The technique is a chemistry technique. Heat something up in a controlled way, watch it lose weight, but what does it do? It gives you a time on your process between T equals 0, T equals T, where T could be 4 years. Okay, so that's the importance of this technique. Again, a simple technique, benchtop, one upstairs in my lab. If you want to know what I'm actually trying to say, here's calcium, bless you, calcium oxalate, and it's heated up, and in a number of stages, this is the temperature axis, this is the weight loss, so that could be 0 to 100% of the actual weight, but in this case it's showing the weight loss coming down, 0 to 60% weight loss. Each temperature gradient that you see loses weight. So if you follow the trace along, along here, then that bit is nothing's happening, then here we've lost something, then here nothing's happening, then here we've lost something, and there's nothing happening, then here we've lost something. 3 specific decompositions. Now if you're doing a process which is a catalyst that's fouled, and then you heat it up, and watch the weight loss, that gives you a time element on the thing here. But if we're thinking chemically, we might be able to figure out what molecules are stuck. That might make us change the catalyst for you engineers to get a better process. That's the hardest lecture you'll actually have, because it's totally out of your comfort zone. You were very good, I have to say. I'm very impressed. The tutorial that comes up next is a tutorial which helps explain these techniques a bit more, gets you into the idea of what they're used for. Those of you who missed last week's tutorial could do last week's tutorial. I am not embarrassed to go through last week's tutorial again, so I'm not embarrassed to have you do it. And I would just like to remind you, that's what you've done. The tutorial rooms are now on D floor, Reynolds D1, Reynolds D2. Demonstrators will be up there.